An Orion capsule of the Artemis II mission flies over a gray landscape riddled with craters and illuminated by the relentless sun. Why does the moon permanently hide half of its surface from our eyes? The answer involves a billion-year gravitational break and the incandescent past of our own planet. On April 6, 2026, the Artemis II mission plunged into the moon's radio shadow, passing the far side on a free return trajectory without entering orbit. The crew witnessed a terrain radically different from the silver disk that illuminates our nights. There are no dark basalt plains, no leveled seas where ancient Apollo missions made their landings. Instead, the ship's instruments recorded a chaotic crust, scarred by deep impacts and mountain ranges that overlap in a labyrinth of ancient rock. At this exact moment of flyover, communication with mission control ceases completely. It's a region where radio silence with Earth is absolute, dictated by the sheer mass of the celestial body blocking electromagnetic signals. Telemetry marked the most distant point ever reached by a crewed spacecraft, 400,171 kilometers from home, an absolute distance record that surpassed Apollo 13's historic mark. And the alien landscape unfolding beneath Orion's windows was not a formation accident. It's the result of an orbital dance that began when the inner solar system was still organizing itself. This orbital dance kept the far side in complete anonymity for almost all of human civilization's history. Until October 1959, no eye or lens had captured a single beam of light reflected from that hemisphere. It was the Soviet probe Luna 3 that changed this paradigm. The spacecraft used a complex mechanical system that photographed, developed, fixed, and dried the photographic film on board, transmitting the images by radio back to Earth. The first grainy photographs revealed an unrecognizable terrain, which shocked astronomers of the time. 9 years later, on December 24, 1968, the Apollo 8 crew became the first to see this topography with their own eyes. Unlike Artemis II's flyover trajectory, Apollo 8 performed an engine burn on the far side to enter lunar orbit. They completed 10 orbits around the moon, and what astronauts Frank Borman, Jim Lovely, and Bill Anders reported back to Houston defied visual expectations. The far hemisphere seemed an entirely different world, rough, bright, densely fractured, and lacking the familiar features we use to guide ourselves with the naked eye. Later topographic measurements confirmed the discrepancy mathematically. The lunar maria, the vast dark patches of solidified lava visible from Earth, cover about 31% of the near side, but on the far side, they represent only 1% of the entire surface. The near total absence of these dark maria is intrinsically linked to why we only ever see one side of our satellite. The mechanical phenomenon behind this is known in astrophysics as synchronous rotation. The moon takes exactly 27.3 days to complete one orbital revolution around Earth, and it takes the same 27.3 days to rotate once around its own axis. This mathematical precision isn't a cosmic coincidence, but a direct consequence of gravitational friction. The moon isn't a perfect sphere. It possesses a slight elongation, an equatorial bulge of rock created by our planet's relentless pull. Over billions of years, Earth's gravity continuously pulled on this bulge, acting as a constant brake on lunar rotation. Internal friction within the rocky layers dissipated the Moon's rotational energy as heat, slowing its spin millennium after millennium. The process continued until the Moon's rotation locked into exact synchronicity with its orbit. It's a state of permanent mechanical equilibrium, forever aligning the same hemisphere in our direction. As a result of the rigid laws of angular momentum conservation, while lunar rotation stopped decelerating, energy was transferred to the orbit. Today, the laser mirrors left by the Apollo missions confirmed that the Moon continues to drift away from Earth at a rate of 3.8 centimeters per year. But this gravitational locking created one of modern astronomy's greatest misunderstandings. The popular idea of a dark side of the Moon is an absolute geographical myth. What truly shaped this far side to be so different from the one we know? As the Moon orbits Earth, both sides receive sunlight in alternating 2-week terrestrial periods. When we see a new moon in the night sky, plunged into shadow, the far side is receiving direct, bright, uninterrupted sunlight. The real structural difference isn't in illumination, but in the quantity and thickness of rock. In 2012, NASA's Grail mission mapped the Moon's gravitational field with unparalleled precision. Altimetry data collected by the twin probes Ebb and Flow revealed a profound asymmetry beneath the regolith. The far side's crust is significantly thicker than the Earth-facing side, a difference amounting to 15 extra kilometers of solid rock. And this massive rock barrier, invisible to terrestrial telescopes, was the structural key to understanding the absence of the dark maria that Apollo 8 observed in 1968. The origin of this massive rock barrier demands a step back in time to the earliest days of the Earth-Moon system. The answer lies in cooling dynamics and extreme heat transfer. Soon after the formation of the Moon through the cataclysmic impact of a Mars-sized celestial body roughly 4.5 billion years ago, the newborn Earth was a global ocean of incandescent magma. Our planet radiated extreme heat into space, reaching surface temperatures exceeding 2,500 degrees Celsius. The Moon, orbiting much closer than today and already gravitationally locked by synchronous rotation, kept its near side facing this planetary furnace. As a result of this proximity, the Earth-facing hemisphere was continuously baked, remaining in a molten state for much longer. In the frigid dark of space, with its back to the scorching glow of primordial Earth, the far side cooled much faster. Light silicate minerals like feldspar floated to the top of the lunar magma ocean, crystallizing and forming a rigid, deep crust. When large asteroids collided with the Moon in subsequent eons, impacts on the near side easily pierced the thin crust, allowing magma from the lunar mantle to flood the impact basins, cooling to form the dark basalt patches we call lunar maria. On the far side, the crust was too thick and resilient. Even the South Pole Aitken Basin, one of the solar system's largest and oldest impact craters, couldn't pierce the geological floor deeply enough to release the dark basalt. The overlapping craters of the far side are an intact geological record of a violent time that the near side erased beneath layers of solidified magma. The Moon permanently hides this half because Earth's gravitational pull braked its rotation to relative rest, and its appearance is drastically different because the heat of primordial Earth cooked the near side, allowing the far side to build an impenetrable rock shield. The asymmetry that Artemis II documented in its distance record isn't just a topographical curiosity of our natural satellite. It's a thermal scar of our own origin, a mirror of dust and rock that reflects the incandescent fury of an Earth that long ago ceased to exist.
In our next episode, we'll investigate Voyager 1, the most distant human probe, and what it's still sending. Billions of kilometers from home, a small golden disk carries the sound of Earth's tides as it glides, in silence, through the interstellar dark.